Okay, can you, excuse me, can you all hear me? Okay, so I'm back. So I want to do one more example where I apply Gauss's law. Like I said, there's really a limited number of problems that we can do. By the way, let me go back to this problem again. I mean, I did a line charge, but you can also do this if you replace the rod with a cylinder. Okay, you can do the same thing with a cylinder too, because the cylinder has the same symmetry as a rod. So if you either have a solid cylinder or a hollow cylinder, you would use the same approach as the first two problems I did, except that your Gaussian surface is a cylinder. Okay. Let's go to this last one. This time we're doing a plane, an infinite plane. Why are we choosing an infinite plane? Because it has a sufficient symmetry that where you can use Gauss's law. And it turns out when you do the plane is the easiest one to do in terms of the math. So let's say we have a positively charged plate is infinitely big. I mean, I can't draw an infinitely big plate, so I just drew this. Okay, so let's say it's positively charged. I mean, just imagine what the field line, excuse me, what the field lines would look like if I have a bunch of positive charges real close to each other. Those positive charges would form a plane. And the field lines would look like this. Okay, I'm not going to draw all of them. In fact, the field would be uniform. I don't know if you remember the field lines I drew for two positive charges. I showed you for two positive charges. They were separated a certain distance. The field lines in between them kind of curved away from each other. If you put them real close together, you're going to form field lines like this. And just imagine putting them in a two-dimensional lattice. Okay. So this thing comes out towards us. What shape should I use then for a Gaussian surface? Because I cannot use a sphere, right? Because if I have field lines like this, and then I draw a sphere, I cannot pull this thing out of the integral. Okay? It turns out I'm going to use a cylinder, a short cylinder with a huge cross-sectional area. Of course, I cannot draw a cylinder with an infinite cross-sectional area, so I'm going to draw a small one and pretend that it's the cross-sectional area is infinite. Okay, so I'm going to draw a cylinder like this. So no field lines penetrate the lateral surface. When we did the line, we only did the lateral surface. When we do the plane, we do the ends. And usually we draw this so that the cylinder is short but has an infinite area. Whereas when we do the line charge, we draw it infinitely long with whatever area, cross-sectional area we need. But here this area has to be infinitely big, like the same size as the plane. Okay? Although I'm not drawing it that way because I can't draw an infinitely large cross-section. And you notice that the electric field is parallel to the normal to each of these guys. And so then when I do my integration, I can pull this thing out still. And on both sides, the electric field and the normal to the surfaces are parallel to each other. So I have two surfaces I have to consider. And I'm not going to call the areas, I'm not going to say the area of that cylinder is pi r squared. I'm just going to call it A, if you guys don't mind. Okay? And so when I write this out, I get that. But there are two ends. Each end has area A. So I'm going to have E times A plus E times A. And it's always plus because these two vectors here are parallel to each other, and these two vectors here are parallel to each other. And again, remember the dot product. If theta is 0, then in both cases, because that theta is the angle between the two vectors, then I'm going to get E times A plus E times A. And that's going to be equal to the total charge enclosed over epsilon r. And again, you're saying, well, you have an infinite amount of charge because it's an infinite plate. Well, the amount of charge enclosed, remember, this is same cross-sectional area as the plane, even though I didn't draw that. That's going to be the surface charge density times the area of the plate. So I have E times A plus E times A is 2E times A. The A's cancel. And so the electric field is sigma over 2 epsilon naught. That's it. Okay? That's the electric field due to an infinite plane. Now, in the modules, I have a problem where I calculate the field due to a disk. The disk is uniformly charged with charge density sigma. If you take that expression in the limit when you're really close to the disk, or when the disk radius is huge, that equation in the video approaches this expression. Just take a look at it and you'll see. Okay? What if, just for fun, I'm just adding something here. If I know this is the field due to a plane, what if I have two planes next to each other? Suppose I have a positively charged plate here and a negatively charged plate here. Let's pretend that their dimensions are way bigger than their separation. If that's the case, then those plates can be treated as infinitely large, and I can use the expression for the field to parallel to a plate. Let's draw the field lines for each one of these. I will use red for this one. The field lines point away. So the red, this is the red. Let me draw the field lines for the other one. in blue. Field lines always point towards a positive charge. Field lines always point towards a negative charge. Sorry about that. Okay, I'm going to stop drawing these. But what happens to these fields outside? What happened to the field lines here? What do you notice? These are in opposite directions. Since they're the same plate, the sigmas are equal but opposite. The fields here cancel, and the fields here cancel, but the field here doubles that. These two fields are in the same. All the blue and the red here are in the same direction. So the field gets doubled in between, but cancel outside. And what I'm using is a principle of superposition to calculate the field. So in between here, the field is twice this number. Okay? Out here, the fields cancel. It gets 0. So 0 field, twice the field here. You have homework problems where you have like 2, 3 plates, etc. to be able to do these. So you need to be able to draw this. And we're just using the principle of superposition. Yeah, so they cancel here and they cancel here, but here they add. In between they add, but to the left and to the right. To the left of the positive plane and to the right of the negative plane, they cancel. And the reason why is because I made the charge density equal but opposite. Obviously, if they weren't equal but opposite, that wouldn't be the case. Okay. Again, I use the principle of linear superposition. I can add fields. And I can do the case where I make them perpendicular to each other too, and just add them as vectors. One's going to point in the x direction, one's going to point in y direction. Okay. So last topic in this chapter. And there's some miscellaneous things. Let's talk about equilibrium. You guys all know what equilibrium means. If you had Physics A with me, you learned it. When you had Physics 205 or 105, you've learned it. So equilibrium means that the sum of the forces equals 0. I want to consider equilibrium involving fields only. Okay, I want to look at equilibrium involving fields only. So equilibrium means the sum of the forces equals 0. Or, in this case, we're looking at fields. That means the sum of the Q times E's equals 0. If this is 0, then E net has to be 0. Because Q times E is force. If the sum of the forces equals 0, the total field has to be 0 at that location. So when a charge is in static equilibrium, E has to be 0 at that location, since F equals Q times E. If I have something that's under the influence just of electric forces, if the system is in stable equilibrium, if I move the object to the left or to the right, there should be a force restoring it to equilibrium position if the equilibrium is stable. I'll give you an example. Suppose I have a ball in the bowl. Let's do gravity. This ball is in equilibrium and sum of the forces equals 0. if I move this to the left or to the right, what's going to happen? If I push it to the left, there's going to be a force to the right, making it want to go towards what was that. If I pull it to the left, it'll want to go back to the right. And so that's a stable equilibrium. If I have this ball on top of a hill, if I give it a push to the left, it's going to go down the hill. If I give it a push to the right, it's going to go down the hill. That's an unstable equilibrium. So it turns out that in the case of electric fields, the equilibrium involving electric fields is always unstable. Okay? Equilibrium involving static fields is always unstable. However, again, remember the caveat here is that I'm only talking about particles under the influence of Coulomb forces. Okay? So I just want to mention that. It's just something I want to mention briefly. Let's look at conductors in equilibrium. I have a conductor. Again, what's a conductor? Well, the electrons in a conductor are free to move. So this is going to be a special discussion. Conductors have a different behavior, and they're much more difficult to deal with. All the problems we've done so far involve insulators. Conductors are much more complicated. Okay? If you have a conductor that's in equilibrium, the field inside the conductor has to be zero. The field everywhere in the conductor must be zero. Why? Because F is Q times E. If E is not zero, F is not zero. So if you have a conductor in equilibrium, by definition, E has to be zero inside. If you have a conductor in equilibrium and it has a net charge, any net charge has to reside on its surface. And in fact, that field then that's on the surface is always going to be perpendicular to the surface of the conductor. So what will happen is if I charge this up, remember a conductor, then whatever charge it has to reside on the surface. And the field always points perpendicular to the surface. Normal to the surface. And the charge density is greatest at the sharpest point of a surface, because the charges can't move around very well. So let's go through this. So when a conductor is placed in equilibrium, the charges have to redistribute themselves until the sum of the forces equals zero. Until E equals zero. Otherwise, the conductor is not in equilibrium. Charges will be moving. Equilibrium means that the charges aren't moving. The charges inside here ain't moving. Okay? If I take this thing and put it, this charged object, and put it in an electric field, the charges will rearrange themselves so that the field inside is zero. And whatever charge is on there will exist on the outside. It'll actually create a field inside it to cancel the field that's outside. And it does this very quickly, like 10 to the minus 16 seconds. Now, I can use Gauss's law to show that if I put any charge on this thing, conductor, remember, conductor, not an insulator, whatever charge I put on this thing will reside on the surface. It's easy to prove because if this is an equilibrium, and let me draw my any Gaussian surface. If this is an equilibrium, the electric field has to be zero inside. Okay, everywhere. Well, if this electric field is zero, if this thing is zero, the whole integral is zero. If the whole integral is zero, Q is zero. And so I can make this imaginary surface bigger and bigger and bigger and bigger until I get to the surface of the insulator, the conductor, sorry. Once I get to the surface of the conductor, the electric field then won't be zero, and that's going to tell me all the charges on the surface of the conductor. Okay, so I can make this Gaussian surface bigger and bigger and bigger. This will always be zero inside until I get to the surface. Now, on the surface, the electric field has to be perpendicular to the surface. It cannot have a component of electric field, let's say, along the surface. You cannot have that. Because what happens to a charge if the electric field is a component like that? If I put a charged particle here, it's going to want to move either in the direction of the electric field or opposite the direction of the electric field. That contradicts the fact that we have a conductor in equilibrium. Now, what can we say about the field at the surface of the conductor? So I use Gauss's law. Say, okay, let's draw a little pill box, my cylinder with a big area, my short cylinder. So let me draw something like this. I want to apply this on this side and this side. Remember, there's no electric field coming through here. The electric field, I'm making the area so that I only have the field lines going through here. So the electric field here I'll call E2. The electric here I'll call E1. So I want to do this integral. I'm going to have an E times A here and an E times A here. But what's E inside this thing? Isn't electric field inside zero? Yeah. So then my integral is going to just give me E2 times A equals Q enclosed over epsilon naught. But Q enclosed is sigma times A. So then the electric field on the surface is going to be sigma times A, sigma over epsilon naught. The A's will cancel. This, let me blow that up. And I got this out of an old textbook. There's two conductors in oil, and there's threads in the oil. The two conductors are charged. Look at the field lines inside the circular conductor. There are none. Look at how the field lines are shaped. Okay, when you look inside the conductors, the ring, there's nothing inside there. And there's no field in the conducting material itself. Okay. Now, one more thing I'm going to say, and I cannot prove this rigorously here, but if you have a conductor with sharp surfaces, the charge density near the sharp surfaces will be greatest where the radius is least. In fact, the electric field will be greatest where the radius is least. And that's because the charges cannot move very easily around sharp points. I'm giving you a hand-waving argument. If we have time, I can give you a better argument in the next chapter. But I'm just giving you a kind of a hand-waving argument. That's why, like lightning rods work, right? The field at a sharp point is very high because the charge density is very high. Here's an example of the field lines around a sharp point. Look at the field lines around the sharp point, and then field lines everywhere else. They're very bunched close together around the sharp point. Okay, I wanted, before I do this example, this is the last example in the chapter. Kind of encompasses everything with conductors, etc. I want to do a demo, and I apologize. It hasn't been working very well, but our Van de Graaff is in bad shape. But I'm going to try it. I'm going to try to show something. I haven't done any demos yet. And I have to be as far away from my computer as possible because the Van de Graaff, one of my colleagues used the Van de Graaff in the classroom many years ago and blew out the sound card. Blew out the sound card because of the high voltage this generates. Okay, so I need to be careful. Give me 1 second. And I'm going to take the camera and point it better towards here. So I'm going to mess around with the magnification, so just give me a second. So you should see a cage. Let me set up so you can see 3 balls. You should see 3 balls in it. Do you see 3 balls in there? There's one outside and one in between the 2 cages, and then there's one inside the main cage. The ball here, a ball between these 2 cages, and then the ball in the center. You guys can see that? Okay. And so, to demonstrate the charge stays on the outside of the conductor, I'm going to do the following. I'm going to tie these 2 together electrically. And I'm going to crank up the Van de Graaff. And I can tell if something's leaking somewhere. I can hear it, charge leaking. But do you notice that this one ball on the outside is starting to move? Actually, the way I've set it up, the ball in the middle should start moving, but it's not. I don't know, because I'm losing charge. You see the one on the outside, how it's being repelled? It's actually being repelled. It's actually getting charged up because the air is breaking down and arcing to the ball. And usually if I have enough charge on the Van de Graaff, I can hear stuff leaking. I don't know if you guys can hear it. That ball will actually bounce back and forth. Okay. Now this other ball in the middle, this one here, should be bouncing between these two. And it's not because I'm losing charge. Okay. So I really basically what I want to demonstrate is that all the charge will reside on the conductor, on the surface of the conductor, but it's not happening. Actually, I'm wrong. Nothing should happen in this case. Sorry about that. These two are connected together, and so all the charge should be out here. So all the charge should be out here, okay, because I connect them together. So now I'm going to turn this off, and I have to discharge it. Otherwise, I'm going to get zapped. That's not good. I'm losing a lot of charge. Now when I take this off, see what happens. This thing is acting as a shield. I can touch it because I got an insulator. This is acting as a shield. I wish this would work better. By the way, while I'm at it, I have this bulb. Let me change the view and show you the effect of the Van de Graaff on the bulb. The field's very high. Oh, that bulb's dead. Hold on, let me turn that off. Let me try it again. Okay, now let's try it. Oh, I can't see any. I don't know if you can see the light go on. Can you see the? Can you see? It's a dull orange. If I turn out the lights, it'll be too dark in here. But let me try it anyway, just for fun. Can you see a flicker of orange? Or is that too dark? Do you see the orange? Okay. It's lighting up a lot? Okay, good. That's good. And so the field is actually ionizing the gas in here. I mean, not ionizing, exciting the gas in here. Making the neon light go bright. And if I put the ball perpendicular to the electric field, it wouldn't go on at all. And I might do this demo again in the next chapter. Okay, let me go back. So I'm magnify way too much. All right, let me move the Van de Graaff. I was afraid of doing this demo because of my computer. Usually I take the computer out of the classroom when I do this. Okay. So let's do one last example in this chapter. And this example pretty much summarizes everything in the chapter. And let me show you the problem. This is the problem we want to do. So we have a solid insulating sphere of radius A. That's the sphere that's inside. It's inside a conducting spherical shell of radius B. Don't worry about how this was put together. Okay, I know that sounds kind of weird how that's put together, but the conductor is inner radius B and outer radius C, and as it's charged with a minus Q. What I want to do is determine the electric field everywhere. Okay, I want to find a field everywhere. And you have a couple of problems like this in the homework. Let me draw my system. This is a conductor. Okay, and the red's an insulator. I want to find a field everywhere, but let's talk about what happens when I set this up. This has charge plus 3Q. This has charge minus Q. But when I set this up, the charge in the conductor is going to rearrange itself because the electrons are free to move. And in fact, this conductor is going to be in equilibrium, so the total field in here has got to be 0. How will the charge rearrange itself so that the total field inside here is 0? Well, I'll give you a hint with Gauss's law. So let me draw a Gaussian surface. The field inside the metal has to be 0. The field at that location where I drew the black dotted line has to be 0. So on that dotted line, this is 0. How can it be 0? Because I have 3Q inside. Well, what must happen is when this is inside, that's going to draw in negative charge on the inner surface of the sphere. So what happens is negative charge is drawn in on the inner surface of the conducting, I'll just say the conductor, the conducting sphere. Okay, how much charge? Enough charge so that what's enclosed is 0. Well, if this is plus 3q, whatever's around here is got to be minus 3q. Well, if minus 3q gets drawn in here, so I have minus charge all the way around this thing. Equal and opposite to this one. That must come from somewhere in here. That's gotta leave a plus 2q on the outside. Why must it be plus 2q? Because remember this conductor had minus q of charge. Plus 2 minus 3 is minus q, right? Plus 2q minus 3q is minus q. Okay? So having said that, I know what the charge is everywhere. I can start using Gauss's law to find the field everywhere. Let's start out here. And realistically, if I'm outside here, if I'm standing over here at point P, okay, we're looking for R greater than or equal to C. We're trying to find the field there. That thing looks like a point charge. If I were to see, how much charge am I going to see there? Well, I'm going to see 2q. If I drew a Gaussian surface all the way around this thing, the total charge would be plus 2q. And so the field then kq over, k times 2q over r squared. Because if I want to use Gauss's law to do this and write it in terms of epsilon, okay, so I would use this integral. I would have e times the integral of dA equals the charge enclosed, which is going to be 2q over epsilon naught. And so E ends up to 2q over 4 pi epsilon naught r squared. Of course, 1 over 4 pi epsilon naught is k. Now, what about the field between B and C? What about the field between B and C? You're inside the conductor, so E is 0. Okay? You're inside a conductor, so E is 0. Actually, this should be equal, because on the surface it's 0. Now what about over here? R between A and B. Well, that one's easy because see this purple Gaussian surface? How much charge is inside this purple Gaussian surface? 3Q. And so the electric field, I can write it two different ways. And now for R less than or equal to A. What do I do? Well, I draw a Gaussian surface inside here. And I got to do that integral. I got to do the sphere integral like I did before. Now this thing is uniformly charged. So let's do this integral carefully again to get another example of doing the sphere. Okay. Let me get a good marker here. I want to use this, and again, if I use Gauss's law, my E dot n is easy. I can pull it out of the integral. This is going to be E times dA. This is going to be 4 pi r squared like I did before. But now I got to find how much charge is inside this uniformly charged purple sphere of radius r. And this is uniform charge density. So if it's uniform charge density, then rho is going to be 3q over 4 pi, or 4/3. What's the radius of this thing? Pi a cubed. That's the density, right? Charge over volume is density. And then this is going to be, the dV is going to be 4 pi r squared dr. And I'm going to integrate from 0 to r, and I'm going to have a problem with my variables. There's too many r's here. I'm going to call this up my dummy variable, r prime. And so this is going to give me E times 4 pi r squared equals 1 over epsilon naught. As the integral from 0 to r. Oh, let me pull out all the constants. Hold on a second. Again, I just put these primes there to make it different from this. That's all. It's just a technicality. There's nothing other than that, just a technicality. Okay, so this becomes r cubed over 3. This r squared cancels with 2 of those. This 4 pi cancels with this 4 pi. And so E is equal to the density times r over 3 epsilon naught. But that's the density. So this cancels with this. And I get 3qr over 4 pi epsilon naught a cubed. And so the electric field then is going to be 3qr over 4 pi epsilon naught a cubed. And notice when you're at the surface, when r equals a, these two match. The reason why they match is because there's no charge on the surface of the sphere. There's no charge, there's no surface charge density. As opposed to here and here, there is a surface charge density. In other words, you sucked in some charge when you put this guy inside. So what does the field look like if I made a graph of the electric field as a function of r? Well, for r less than a, it's going to be linearly dependent on r. Then it's going to go as 1 over r squared. Then what? Then e equals 0 between b and c. And this is open, sorry. And then what? Then it jumps up to 2kq over r squared. That's an open circle. That's what the field looks like. The discontinuity tells you have a charge on the surface. Okay? Questions? Concerns about that one? If you can do this one, you can probably do any problem in the chapter. I'm sorry, I missed that. Okay. All right, so I'm done with chapter 24. And now I want to begin with chapter 25. By the way, normally I do a few more demos, but because of the way we're set up online and playing around with the Van de Graaff is kind of a issue with my computer, so I haven't been doing as many demos as I usually do. Okay, so I'm going to switch my PowerPoint to chapter 25. Just give me a second. And this is the last of this abstract kind of unit. But it's an important unit. So I'm going to introduce another topic in this chapter that's supposed to help us solve electrostatics problems. At least the basic problems. Okay, so this chapter is on electrical potential energy. And so we're going to do calculations for discrete and continuous charges. But these calculations are a little bit easier because you don't have to figure out r hat. Because these quantities in this chapter are scalars, they're not vectors. It's a little bit easier. Okay. A little bit easier to understand. But this topic has a lot of applications because it's going to have applications when we talk about circuits and applications basically in all the units that we cover from now on. And so it is an important topic. So we're going to define potential, and we're going to do some calculations with them. Now, how do you calculate electric potential for discrete charge distributions and continuous charge distributions? That's going to be our goal. And then we're going to look at some applications. In fact, I have a lot more in there than I normally do. Usually I don't have time to cover everything I have in there because I have some special examples. Sorry I wrote in this box. You guys can't see when I wrote below here. Sorry about that. Okay. Let's talk about briefly characteristics of the electric force. The electric force and the gravitational force are similar because they're proportional to 1 over r squared. Where r is the vector that goes from the source of the field to the point in which you're calculating the field. Okay? Forces that have this form, it doesn't have to be 1 over r squared, forces that are directed radially, they're called central forces. And the integral of the force over a path only depends on where you began, where you started, when you ended. It only depends on the endpoints. That's what you learn with gravity. So if you want to calculate the work done by the force, the work done only depends on the endpoints. That's it. Doesn't depend on the path. It depends on where you started and where you ended. Okay? So if you ended up where you started, the work done would be 0. That's what you learn in gravity. And in fact, because of that, you were able to define a gravitational potential energy. Okay? Because the integral only depends on the endpoints, if you ended up where you started from, if you integrate over a closed path, if you integrate the electric force over a closed path, you get 0. Just like the gravitational force. If you remember, if you take an object and you raise it up to here and then bring it back down, the work done by gravity is 0. Okay? So the work done in closed path is 0. And that allows you to define a potential energy. And in Physics 205, you said that the work done by the gravitational force is minus the change in potential energy. That's what you learned in 205. So we're going to do the same thing here. We're going to say that the work done by the electric force is minus the change in potential energy. So we're going to say this, that the work done by the electric force over not a closed path, we're going to say it's minus the change in potential energy. So that means then that delta U is equal to minus the work done by the electric force and the electric force is Q times Z. And for dealing with point charges, then we write so the change in potential energy Using the same ideas, the same general ideas that we use in Physics 205. And so you're integrating from between points A and B, and I didn't write the endpoints. Okay, so it's the integral between 2 points. Gives you a change of potential energy. For gravity, this would be the letter G. And then this would be a mass. By the way, one thing I forgot to tell you, there's a Gauss's law for gravity. We usually don't talk about it. And the next topic I'm going to talk about today, there is a version for gravity, but we usually don't talk about it. And I'm going to skip this video just because of the fact that we're online. But I want to define something else. I want to define the potential energy per unit charge. I want to define delta U over Q. Okay, I want to define that. And we call that the electrical potential difference. So V is, well, let's do it this way. Delta V is delta U over Q, and we can say V is U over Q. And it's a scalar quantity. It's the electrical potential energy per unit charge. You can do it per unit mass for gravity, but we usually don't talk about it. The unit is called a volt. So this is based on what I talked about on last Friday in lab. Okay? So this is the electrical potential difference in electrical potential. When people work with circuits, they always call it voltage. Or you really should say the potential difference. Or the electrical potential difference. Okay, I'm not going to show you the videos because I have to then blur them out on YouTube. So we can describe, we can think about the delta V as the work per unit charge necessary to move an object from point A to B, or in the presence of an external field. An analogy is this. If I have a marker on my desk and I raise it, the work that I do has increased the potential energy. The work that I do is minus the work that gravity did. Isn't that true? The work done by gravity is minus mgd. The work that I do is mgd. So when I move this marker from the table up to here, I have added energy to the system. I've added potential energy. I can talk about the amount of potential energy per unit mass that I've added to this marker. We would call it the gravitational potential. Well, it's the same idea with the electrical potential. Okay? The electrical potential difference is the work per unit charge some external force must do on a charge in the presence of an electric field. So if I move so in the case of gravity, if I move an object from here to here, the total work is done. What forces do work? The work that I do and the work that gravity does. The sum of those two is 0 based on the work kinetic energy theorem. So the work that the applied force does plus the work done by the field is 0. So in the case of if me lifting up an object, I do this much work, gravity does this much work, as long as the change in kinetic energy is 0. In the case of the electric force, let's say it's uniform, then this would be QED, and this would be minus QED. Okay? So that means that the work done by, or delta U, is minus W field and W applied in this case furthermore, this is going to be equal to Q delta V. Just look at this. Very easy to get confused with the signs. Now, what if the field is constant? Suppose the field is constant. And let's look at the work done by the field. Okay? The work done by the field is the work done by Q times E. If the field is constant, I shouldn't say constant, uniform. And I should change that in my notes. Then this becomes where D is the distance it traveled. If theta is 0, then the work done by the field is Q times the electric field times D. But that's going to be equal to minus delta U. And that's going to be equal to minus Q delta V based on this relationship. So I have minus Q delta V equals QED. The Q's cancel, and E is delta V over D, negative delta V over D. So what does this say? I'm doing this in a very special case. It says that the electric field is in the direction of decreasing V. Okay. The electric field Furthermore, it says if you have a delta V, you have an electric field. Okay, if you have a delta V, you have an electric field. That's another thing to look at. Now, I did it for the simple case. I'll do a more general case next time. Okay, I think I'm going to stop here now that I introduced the topic. So you might want to look at the beginning of chapter 25. Next week I'll do all of chapter 25. Okay, so next week is what? Today is the 20th or 21st. Okay, so I'll do all of that next week. I should be able to finish all of it next week. Okay. So I'm going to stop here. Questions, concerns? How are you guys all doing? Are you hanging in there? Are you still there? Yeah, and Scott, it is. I mean, the new stuff is a little bit confusing. I think it helps when you start doing the homework. Well, that's good if you're understanding the older stuff better. As you do the homework, things will get better. You know, and I really recommend that you do maybe 3-4 problems a night. I've noticed that I go on WebAssign and a lot of people haven't started the homework until a couple days before it's due. That's not going to work for you. I think it's better if you do about a couple problems a night. You do the easier ones first, and then as you learn the material better, you can do the harder ones. Right? Or you can think of it this way: do the ones you know how to do first, and then attack the harder ones later. Okay. And and that makes you go through the material over and over again, and it starts to make more sense. Okay. All right. So we will see you. Well, I won't see you on Friday. I'll see you next week. So don't forget, we will meet on Friday, but it'll be Professor Shakel, not me. Okay? All right. You all take care.